This section is going to be covering the area between two curves. And so we have used the integral so far to represent the area between a curve and the x-axis. Now we're going to discuss how to find the area between two curves on a coordinate plane. And sometimes your curves are going to intersect, and sometimes the area is going to be defined as being between two vertical lines, or could be horizontal lines, depending upon the orientation of your curves. So for example, the things that we have done in the past, when you found an integral, what you were finding was the area between the curve and the x-axis. So for example, the blue curve here, if we did an integral of that blue curve, that would give you this area. Now if we did the integral of the yellow curve, that would give us this area right in here. And so if we want the area between the two curves, what you would end up doing then is subtracting the yellow area from that pink area, which will give us the area between our two curves. So that's kind of what we are going to be doing with this. All right, so this is a representative rectangle here. And with this representative rectangle, we can see from our integrals the length of this part of the rectangle is going to be delta x, which is your dx part of your integral. And then the height of the rectangle is going to be the distance from one function to the other function. And you find that distance by taking the largest or the highest point and subtracting the lowest point. And that would give you the length of this. So what you're going to have then is going to be the integral from a to b of f of x minus g of x, as long as f of x is your function that is above g of x. Sometimes your rectangles will be oriented horizontally, and we'll take a look at that in a little bit. All right, so let's find the area of the region bounded by y equals negative x, which is this right here, and y equals x squared plus 2, which is this curve right up here. So to find the area, we're going to set up our integral. This integral is going to go between 0 and 1, as you can see here and here. And the top function is going to be x squared plus 2 minus the bottom function, which is negative x, and dx on the end. All right, so we're going to clean this up a little bit before we evaluate this integral. So you're going to have x squared plus x plus 2 dx. Take the antiderivative, giving you x cubed over 3 plus x squared over 2 plus 2x. We evaluate all of this between 0 and 1. So substituting 1, you're going to get 1/3 plus 1/2 plus 2 minus, and then substituting 0 in, all three of your terms will be 0. All right, so what this gives you then will be 2/6 plus 3/6 plus 12/6, which is 17/6. All right, so the next problem says to find the area of the region bounded by f of x equals 2 minus x squared. That is going to be the parabola right here. And g of x is equal to x, which is this line right here. All right, so setting up an integral, we're going to have the integral of the top function, which is 2 minus x squared, minus the bottom function, which is x dx. Now, as far as our boundaries for this integral, that would be between this x value and this x value over here, where these two graphs intersect each other. Those two values were not given to us, so we need to calculate them, and we will do so by taking 2 minus x squared, setting it equal to x to find that point of intersection. It's quadratic, so we set it equal to 0, giving you x squared plus x minus 2, and that's x plus 2 times x minus 1. So x is equal to -2 and positive 1. All right, so that's going to tell us that this intersection is at the x value of -2. This intersection here is at the x value of 1. So that's what we are integrating between, is -2 and 1. So we're going to clean this up a little bit. Integral between -2 and 1 of -x squared minus x plus 2 dx, which will give you -x cubed over 3 minus x squared over 2 plus 2x evaluated between -2 and 1. So substituting 1 in, you're going to get -1/3 minus 1/2 plus 2 minus, and that's going to give us positive 8/3 minus 2 minus 4. So just getting rid of our parentheses, and I'll go ahead and get a common denominator here. Well, I'll wait. This is -1/3 minus 1/2 plus 2 minus 8/3 plus 2 plus 4. So the -1/3 and the -8/3 is -9/3, which is -3. You have a 2, 2, and 4. That gives us 8 minus 1/2. So that's 5 minus 1/2, which is 4 1/2. Now, on this one, we need to find the area of this region. However, we have actually two regions involved here. We have this region here and this region right over here. Again, we do not know the intersection here or here, so that's the first thing we need to take care of, is finding that intersection. So we're going to take -x squared plus 3x, set it equal to 2x cubed minus x squared minus 5x. Set this equal to 0. It's going to give you 2x cubed. The x squareds will cancel. And subtracting 3x will be a minus 8x. Factor out a 2x. Leaves you with x squared minus 4. So x squared minus 4 factors to x plus 2 times x minus 2. All right, so what that gives us then are x values of 0, which we can see here. -2 is over here, and +2, which is right here. Those are our intersection points. All right, so let's go ahead and set up our integral. We're going to have an integral between -2 and 0. That is this region right here. This top function is our cubic graph. Now you can see the cubic graph right here. So the top function is the cubic graph. So that's going to be 2x cubed minus x squared minus 5x minus the bottom function, which is the negative x squared plus 3x. All right, so that whole thing right here is going to give us the area of this region. Now we need to calculate the area of this region, or write an integral for the area of this region, and then we add these two areas together. So this will be plus the integral from 0 to 2. Now the top function on this one is the quadratic. So it's negative x squared plus 3x plus, minus the bottom function, which is 2x cubed minus x squared minus 5x. All right, so you do have to be careful with these because the top function and the bottom function are different. Here, the top function is g of x, whereas over here the top function is f of x. Therefore, you cannot just write one integral between -2 and +2. You have to break it up into two integrals on this. All right, I'm going to let you pause the video for a second and go ahead and evaluate these two things. First thing you want to do is distribute this negative, combine like terms, and then do your antiderivatives on each of these. All right, so at this point, go ahead and pause the video, work it out, and then unpause the video, and you can see the solution that I will write down while you are working on this. All right, so you can compare your answer to the one we have here, where your solution comes out to be 16. All right, so the next problem, we're going to find the area bounded by x is equal to y squared and x is equal to y plus 2. All right, so this time you notice our equations are not just y equals equations, they are x equals equations. X equals y squared is your parabola that opens to the right, and then x equals y plus 2 is your linear equation. All right, so this time what we want to think about are your rectangles. Instead of going vertically, we want to think about them going horizontally. The problem with this vertical rectangle thing is this point right here. The bottom function, when we think about the top function minus the bottom function is not always the same equation. Here, the bottom function is this equation, whereas over here the bottom function is your linear equation. So we could integrate this with respect to x, but if we did that, we would have to break up our area into two regions using this intersection point right here. We could do this region, which would be the integral of this equation minus this equation, that would be the top minus the bottom, plus the integral from here to here of this equation minus the linear equation, because your bottom equation is different than it is over here. So again, you would have to separate this into two integrals and integrate both integrals with respect to x. That is one way of doing this. I'm going to propose a different way, and that is going to be, instead of integrating with respect to x, let's integrate with respect to y. Integrating with respect to y means instead of making our rectangles vertical, we're going to think about our rectangles being horizontally throughout this entire diagram. All I drew was one representative rectangle. You could think of rectangles being right here, right here, right here, down here. You can think of them being all over the place. Now, when we integrated with respect to x, going this direction, the base of your rectangle was dx. When we do our rectangles this way, the base of the rectangle is a small change in y, which means this is a dy situation. All right, so what you're going to have is an integral, and we are going to integrate with respect to y, so you're going to have dy here over on the end. Now, the other thing that keep in mind is instead of doing the top function minus the bottom function, we are going to do the right function minus the left equation. So the right equation minus the left equation, because the right equation is always this line. It's always the same graph, same equation. The left equation is always this parabola, which is always the same equation. So if we integrate with respect to y, that means all we need is one equation or one integral instead of two integrals that are added together. All right, so we're going to do the right equation, which is your y plus 2 minus the left equation, which is y squared. Now, the other thing to keep in mind with integrating with respect to y is no longer are the boundaries going to be x values. The boundaries are going to be the y values. Okay? So what we need to do is find out what are the y values where these two graphs intersect each other. All right, so the y values, we're going to take these equations and set them equal to each other. Gives us y squared minus y minus 2. And that will be y minus 2, y plus 1, and y is equal to 2 and negative 1. So negative 1 is the y value where they intersect. 2 is the y value where they intersect up here. All right, so building our equation then is going to be the integral between negative 1 and positive 2. I'm going to clean this up a little bit before actually doing the antiderivative. This is negative y squared plus y plus 2. The antiderivative will be negative y cubed over 3 plus y squared over 2 plus 2y. Evaluated between negative 1 and 2. All right, so plugging in the 2, you're going to get negative 8/3 plus 2 plus 4 minus, and then plug in negative 1. You will get 1/3 plus 1/2 minus 2. All right, getting rid of our parentheses, we have negative 8/3 plus 6 minus 1/3 minus 1/2 plus 2. Now the negative 8/3 and the negative 1/3 is negative 9/3, which is negative 3. So negative 3 plus 6 is 3, plus 2 is 5. Then we got minus 1/2, giving us 4.5 for the area. All right, so what we want to do here is we want to see if we get the same answer when we integrate with respect to x. So could we have integrated with respect to x? Yes, we could have. Would we get the same answer? Probably. We should, anyways. And so let's go ahead and try doing this the different way, but getting the same answer. So this time we're going to integrate, and we know that the point down here was -1. We know the point up here is 2. Now this coordinate right here, that coordinate, let me find my equation here from the other page. Our two equations were x equals y squared and x equals y plus 2. All right, so if I take my y value of 2 and plug it in over here, that's going to give us an x value of 4 for the intersection. We know this is at 0. All right, so we need to find the intersection right here. All right, well, to do that, we're going to plug in the -1 into our equation here, which will give us +1. -1 plus 2 is +1. We could have put it here also. -1 squared is also +1. So we have +1 for that point. All right, so integrating, we can write our two integrals. The first one will be between 0 and 1 of the top function. Now the equations over here are written in x equals. We would need to convert these to y equals equations. All right, so the first one would be y equals plus or minus square root of x, and the other one would be y equals x minus 2. And so the top equation here, this one will be positive square root of x minus negative square root of x. And so we have positive square root of x minus negative square root of x. That integral will give us the area right here. All right, so now we need an integral to give us the other area, so that's going to be plus the integral from 1 to 4. The top equation is square root x minus the bottom equation, which is our line, x minus 2. All right, I want you to pause the video, take a few minutes, and try to work these two equations, or these two integrals out, and see if you come up with that same answer of 4.5. Pause the video, work the problem out, and then you can unpause the video and see how your solution matches up. All right, so welcome back. So you can check your work here. There's a good bit of algebra involved with simplifying and then substituting in and evaluating. And your answer does come out to be 4.5, which means it does not matter which way we integrate with respect to x or with respect to y. We should end up with the same answer no matter which way we do it. However, one way will definitely be shorter than the other way on this particular problem, and that was integrating with respect to y was much easier than integrating with respect to x. All right, I'm going to go ahead and leave you with this, and you can go ahead and get started working on some practice problems with finding the area between two curves. Remember to do with respect to x, if the top function is always the same function and the bottom equation is always the same equation. Do it with respect to y, if the right equation is always the same right equation and the left graph is always the same left graph. Now, another thing to clue you in is how your equations are written. If your equations are given to you as x equals equations, it will probably be easier to integrate with respect to y. If your equations are given to you as y equals equations, then typically you're going to be integrating with respect to x.